welcome friends. We will have the 15th lecture today in module 3. Here we will talk about some of the risk modeling associated with marine systems. So, let us see risk in marine systems. We will actually have this in 2 lectures. So, this is one. In the last lecture we said that risk management is always evaluated effectively by asking certain number of questions. Have the control measures solved the problem? Did the control measures created any new hazards? Are any new control measures required as recommended by the local or legal authorities, and do the control measures are updated based on the recommendations made by the report. So, therefore, once the control measures are evaluated successfully, or once the let us say risk management program or plan is evaluated successfully, then one can say that hazard assessment will become more efficient. It becomes rather easy. Okay. Subsequently, the hazards identified from the hazard study are then ranked, that is prioritized according to the critical hazard points, and then focus is paid on the most hazardous event or the incident expected in the process line. Hazard controls are then implemented to prevent the major accidents. Effectiveness of these controls are subsequently evaluated, as just now we saw, through inspection and safety review programs. On the whole, we are also focused on fatality risk assessment, what we call as FAR. Fatality risk assessment is one of the important elements of QRA. Of quantitative risk assessment. The unfortunate part about this is it involves lot of uncertainties. This is because due to insufficient data, that is one of the important drawback here. Therefore, generally modeling fatalities is a very complex task. But however, one can interestingly see, if you look at the ratio of fatalities to the ratio of injuries in offshore accident industries, let us say, if you look at the ratio of fatalities to injuries, one can easily see in exploration and production offshore and oil and gas industry sector are able to control this in the ratio of 1:1400. Injuries are of course happening because of the unprecedented, unexpected, unwarranted issues which are happening in the process sector in oil, gas and exploration production, but however, it does not result in fatality. The ratio is about 1:1500 okay, in the last 10 years. So, you can have the reference of this from my own book, which I have indicated in the list of references of this course. Therefore, it is very clear that injury statistics are more than fatalities, and focus should be on reducing injuries, which in turn will reduce fatalities. If the fatality risk is assessed and focused on risk reducing measures, then probably risk of having injuries will also get reduced significantly. So, one can do a statistical analysis on this. statistical analysis of fatality risk is used when there exists sufficient database of accidents. Uncertainties are less extensive in a statistical analysis. Therefore, calculation of fatality risk based on statistical analysis is often used for occupational hazards like offshore and gas industries. So, fatality accident rate are generally expressed in statistical sense in offshore industries. Okay. Alternatively, one can also do phenomena based analysis. To estimate the fatality accident rate. This type of analysis actually includes chain of events, such as cause of fire, fire loads, responses, then effects on personnel. Because of fire loads. So, you try to understand the chain of events in its series, and then based on each phenomena try to work out the fatality accident rate. So, this approach describes the behavior of a person during a major accident. That is an important advantage. The important advantage is this approach includes behavior of a person during major accident. One can ask me a question where it is included, that is what we call as the response psychology. Okay. These analyses have various steps that a person underwent or has to go through in order to save his life in case of major accident. So, all mock drills, near miss events are documented to summarize major steps a person has to undergo in case of an accident, and this data is included in the analysis. That is why we call phenomena based analysis. But this of course has one of the disadvantages as well. One of the major disadvantages of this type of analysis is that there are uncertainties involved in each step. There are uncertainties involved in each step, which makes either the analysis inaccurate, it makes it incomplete, or it makes it highly complex. The third method by which one can do the fatality accident analysis or rate is averaging the FAR values fatality accident rate values are averaged over separate groups. FAR values are averaged over a separate group over a period of time considered in the plant. The groups are categorized on the basis of the departments such as office, process, production, drilling, categorized based on, let us say, the workplace exposure, like office, let us say stores, drilling, production, let us say process, etc. And we all agree that the fatality accident rate varies for each group. What is the main reason for this? The main reason for this is the number of work hour exposure is not uniform. That is number 1. Number 2, the degree of hazard present in each workspace. Is not uniform. Okay. 3, possible near miss events, control mechanisms. I would say even to some extent the training modules extended to workspace are again not uniform. Therefore, it all lead to different FIR for different groups. So, it is not fair enough to work out on fatality accident rate for the entire plant, because there has been certain parameters which actually differentiate them. So, it is always better and judicious to group them and categorize them in such a form depending upon the workplace exposure, then try to find out fatality accident rate of each exposed group. Okay. Understanding this, let us apply these concepts what we understood in this lecture and the last lecture on marine system risk modeling. Risk modeling for marine systems. In the recent past, one can agree with me strongly that there has been a huge development in the offshore industry, in which the surface installations are taken over by offshore installations. Offshore installations mainly consist of floating or fixed installation, which envisage high probability of failure. Common causes which has been seen in the literature for these kind of failures arise essentially from ballast systems, anchoring systems, or loss of buoyancy. So, one can see here in the recent past a large number of offshore installations are taken place, and their failure either during erection or production are mainly due to ballast systems failure, failure of anchoring systems, or failure of or loss of buoyancy. So, let us quickly see what is a ballast system failure and what does it do, what is the consequence of this. Ballast system failure leads to loss of stability. Even under static conditions. it may lead to either a single point failure or multiple points failure, which is more serious. Let us quickly see what are the hazards which arise from ballast failure. Let us see list of hazards that arise from ballast failure. It could be failure of pumps, valves and control systems. It could also arise from operational failure. The hazard could be also from loss of weight due to anchor line failure. Can also arise from or arise during transition of mobile units, like modus etc. Can also arise during loading system. Failure can happen during loading. All these may lead to all of the above, may lead to abnormal situation which affects the stability. Having understood what are the hazards which can arise from a ballast system failure, let us talk about how to select a damage criteria. Criteria, or one can even say scenario. The damage scenario is generally influenced by the relationship between the extent of physical effects, by the relationship between the extent of physical effects, what we call exposure, and the effect of consequences caused by this exposure. Therefore, while we are interested in assessing the damage scenarios which can result in some loss, our focus in fatality assessment rate or risk assessment in marine systems essentially you should converge to effects on human beings. So, the damage scenario or the loss or the consequences should also address their effects on human beings, working in the plant, which may result in either injury or fatality. It can also result in monetary loss of asset or property. It can also damage third party property, etc. So, obviously, we already seen that in case of any damage scenario occurring from the plant in marine systems, which will lead with production of hazardous chemical, the most important and the most common accident which could happen, if at all it happens, could be fire or explosion. Of course, damages caused by impact of vessels on marine platforms on offshore systems are also possible, but they are of a lower order compared to that of the consequences caused by the fire or explosion accidents. So, the moment I say fire and explosion, one of the important consequences of this, as we read earlier, important consequence of fire and explosion is heat radiation. So, one is interested to know what is the effect of heat radiation on human and equipment when it is occurring. So, what is its effect or consequence on human and equipment when it occurs, because that is how we can work out the economic loss or the injury or the fatality, which is one of the important assessment in risk modeling. So, please pay attention to the table shown on the screen now. For different level of heat radiation varying from 1.6 to 37.5, what are various damage levels which can cause damage on people and on equipment are listed here. For example, if heat radiation effect is about 1.6 kilowatt per square meter, it will not cause any discomfort to people even under long exposure. This will absolutely have no effect on the equipment at all till about 10 kilowatt per square meter radiation. However, if the heat radiation increases further and goes as high as 12.5 from 1.6, maybe close to around let us say 8 times or 7 times, in that case it may result in 100% fatality even when you have a short term exposure. However, that kind of radiation will have a minimum energy required for melting of a plastic. It does not cause serious damage to the equipment, but however, it can also cause sufficient damage to the equipments in the major catastrophe if the heat radiation goes as high as 37.5 kilowatt per square meter. So, depending upon the heat radiation emitted during the process of accident, one can always see the consequences of this on human as well as equipment by taking guideline from the specific tabular data. The second issue is could be the duration of exposure. This is intensity. Intensity of heat radiation, let us say in kilowatt per square meter. Second factor could be duration of exposure, and what would have a consequence on human as well as on plants. Please pay attention to the slide shown on the screen now. If you look at the exposure and duration up to 10 seconds for a radiation intensity of 1% lethality in terms of 21.2 kilowatt per square meter, then if you have an intensity of 21.2, it can result in 1% lethality. If the intensity goes to 16, it can cause second degree burns. If it is of the first degree, then intensity required is about 12.5 for an exposure period of about 30 seconds. Obviously, when the exposure duration increases about 3 times, then you can see here even at low radiation compared to the above, you can always have lethality, second degree or first degree burns on human body. So, depending upon the magnitude or intensity of exposure and duration of exposure, one can estimate easily the damage caused or the loss on human life or the damage caused on human life because of such issues. Similarly, on the other hand, if you look at explosion, as an incident or an accident occurring in an offshore platform, In case of vapor cloud explosion, it will cause two physical effects. One, it should result in a flash fire, over the whole length of the explosive gas cloud. It can also result in a blast wave. With typical overpressures, that can circulate around the ignition source, Interestingly, the overpressure which is caused because of the blast wave will also have serious consequences on human. So, the consequences of overpressure on human could be: 1, it can have a direct effect of overpressure in human organs. There can be a direct effect on human organs. Secondly, the effect of debris from the structure can also cause damage to human. Debris that come from the structure as a result of overpressure or blast wave can also cause damage. To human. However, if you look at the direct effect on human organs is more significant in case of overpressure. Interestingly, we have already seen this model that when the pressure change is sudden, the pressure difference that arises can lead to damage of some organs. The extent of damage varies with overpressure along with the factors. So, what are those factors which can factors that influence effect on human due to overpressure? There are many factors which will influence this. 1, position or proximity of the person to the blast source. 2, protection inside a shelter. Is he inside a protected shelter? Thirdly, body mass of the person. So, it is very important that all people should also be trained in terms of their physical consciousnesses. So, they should be able to maintain the physics in such a manner that in case of emergency they should be able to react faster. At the same time, they should be able to save themselves in the minimum time of exposure. The common organs that are affected because of blast wave on human could be eardrum and lungs. As we all agree and understand now, duration of overpressure is also an important factor. Duration of overpressure is also an important factor to look at the consequences caused by this on human organ. Interestingly, if you look at the typical data, the positive overpressure, which we say in the literature as P0, we already seen this model of detonation and deflagration models in the earlier lectures. Positive overpressure P0 typically can last up to 250 milliseconds from minimum duration of 10 milliseconds. Of course, this can have a remarkable effect on human body. While making the estimate of effects of overpressure, generally people make few assumptions. Few assumptions are made while estimating the damage on human or equipment caused due to overpressure. Let us see what are these assumptions. Firstly, overpressure corresponding to value higher than 0.3 bar corresponds to about 50% lethality. The second assumption is P0, let us say above 0.2 bar, but within 0.3 bar, that is 0.3 bar less than P naught less than 0.2 bar can result in about 10% fatalities. P0 less than 0.1 bar would not cause any effect on the public at all. Interestingly, 100% lethality is assumed for all people or for all present under this vapor cloud. During explosion. Okay. So, please pay attention to the damage description caused on human and equipment as a result of overpressure. So, the table explains the peak overpressure values in bar and the damage description. For example, the peak overpressure of 1.7 bar can result in bursting of lungs, whereas a very low value of 0.01 bar can only cause simple cracks in glass and so on, so forth. After understanding the damage effect on equipments and human being caused because of one of the important source of accident, which is fire and explosion, which can occur on offshore drilling platforms and production platforms, one is ultimately interested in landing up in what is called risk picture. We all know that risk is defined as a measure of potential economic loss or human injury in terms of probability of loss or injury occurring to the public, and of course, the magnitude of the loss or injury if it occurs. Risk assessment depends on many factors which characterize quality of risk assessment. The factors that make or that characterize risk assessment could be population at which the plant is located, that could be one important data. Secondly, ignition probabilities, it is necessary that we should know the density of population in a specific area to estimate the consequences and the risk resulting from an incident. The exposed population is often defined using what we call population density. Population densities are therefore an important part of risk assessment for various reasons. The most notable is that the density is typically used to determine the number of people affected by a given incident within a specific hazard area. So, population density is a very important parameter which affects the quality of risk assessment. Sometimes population data are also available in sketchy forms. For example, population density can be averaged over the whole area which may be affected. Alternatively, you can divide the area into subgroups and then a number of segments and find out density for each segment and for individual groups. The second area of interest which will control the character of risk assessment is ignition probability, which actually depends upon the energy of the material released. During explosion or during fire or during chemical explosive index. So, interestingly, one should also look into the material storage and handling systems, because this will also have a relatively high probability of immediate ignition if they have the source of ignition. So, one should also check whether the ignition possibility is immediate or delayed, because immediate ignition will have high probability of accident, whereas delayed ignition can also be determined as a function of cloud area or the location. In general, as the size of the cloud increases, the probability of delayed ignition decreases. Once we lead to assess risk, risk can be now done in two ways. One is individual risk on a human being. So, one can have individual risk which can have an assessment of combining all possible consequences arising from the events. From each failure case in human impact criteria, event frequencies for a particular event are determined. The financial components of risk is also involved, which leads to high economic loss in case of a major accident. While risk can be classified as personal, environmental, asset risk. So, one can do risk classifications as personal, economic and asset risk. Impairment risk. However, immediately one is interested to know the personal risk, what we call as a part of individual risk. Asset risk, of course, can also be subdivided into material damage risk and production delay risk. So, asset risk can be again have two groups. One is the material damage risk. What is the risk that a material will get damaged, and what is the risk that your production will be delayed. However, when we focus on personal risk, one is interested to know the fatality risk, because one can have two kinds of damages. One is the injury, other is fatality. Fatality risk is further classified into platform fatality, individual and societal risk. So, friends, in this lecture we discussed about the different factors that can add to the qualitative characterization of risk assessment, how risk management can be evaluated, what are the factors which will look into the risk picture, what are the different kinds of risk assessment which are generally done in offshore industry or in risk on marine systems, fatality risk, which is one of the worst kind which one is interested to know, can also again have subdivisions as platform fatality risk, individual risk and societal risk. We will also see them in detail in the next lecture. I hope you have understood that how risk management can be handled successfully, and it can be interesting provided your hazard assessment and hazard identification details are accurate and you are able to create a large descriptive database by conducting various types of surveys and reports which are discussed in the previous lectures. Thank you very much.